Hello everyone, my name is Devanand. I am faculty of heat transfer in ESE Engineering Academy, Hyderabad. So in the last session, it means in the last videos, if you watch that previous video, where I talk about the preparation strategies, key what is heat transfer weightage and which books are recommended for the GATE examination. And I told you about the ESE and the GATE exam difference, right? And I also told you, you need to match with the frequency of the examiner, how he thinks and what is the GATE examination. And I told you, just solving the previous GATE, you should not totally rely on that, because if you find in the special heat transfer subjects, the questions are continuously added new questions every year. So of course, suppose there is a 4 questions, 1 or 2 questions you will get from the previous GATE, but 50% of the questions are new, especially in my subject. And once again, whenever I am talking here, that is all only with respect to heat transfer. I can't generalize the statement. My statements are only for heat transfer, right? So hope you are able to see me clearly and you are able to hear me clearly. If it is, please respond in the chat box so that I can understand you are able to hear me. So once again, good evening to everyone. Good evening everyone. Good evening, can you hear me? Okay. Okay, hope you are able to hear me. And remember, today whatever the session I am going to take, I am not going to bore you, or it's not like a key one way. So what we will do, we will learn the concept through the problems. So, and that problems which I not solve in the class, and these are all new questions I took. Okay, so whether you are my student or not student, whether you are ESE Academy student or not student, these questions are totally new, which we not solve in the class. This is just for the, you will get the new experience of the questions. Okay, so please today whatever the questions we are going to solve, take it very positively, try to respond, and I don't bring any calculators, so calculations you have to do and you have to inform, right? So once again, don't worry at all. So this session will be around 1 hour, and I will make sure ki in 1 hour even I am not going to waste your single minute also. So everything we will discuss regarding the heat transfer subject. Okay, are you ready guys? Are you ready to solve numericals? So take book and pen and paper, and with virtual calculator we are going to solve them. Okay, so shall I proceed? Everyone type your message. Okay, right. So I am reading your comments also side by side. So chalo, we'll go now. Okay, now so I'm not going to waste your time. What are the chapters, what is the weightage and all that. This you can see the previous video, right? In this session we are going to talk about direct questions. Okay, chalo, read this question. This is for I'm expecting this is for 1 mark question, and make sure this is the MSQ. Okay, so please try to understand, this is multiple select question, MSQ. Now read the question and try to give answer. What is the question? The first question is, which of the following statement or statements, okay, is or are true about the black body? So he is saying that which of the following statement is true or are true. So there is a possibility that answer is more than one option. So that's what I told you. This is MSQ. Okay, this is MSQ. So what is the question? Which of the following statement is or true about the black body? So here the important hint is important. So here important is the black body. So if you are good at fundamentals, especially for black body, then you are able to solve this question. But suppose if you know only superficial about the black body, then you can't handle this question. Believe me, this question looks to be easy but not easy. If you know the black body concept very well, then only you can. Okay, anyone try this? Anyone try this? Okay, chalo. Okay, listen. Which of the following statement is are true about the black body radiation? So option A, what the option A is all about? Among all radiation emitted by an ideal black body at a room temperature, the most intense radiation fall in the visible spectrum light. Now, listen carefully. Suppose if you take Wien's displacement law, okay, for black body. So what does it mean? Lambda T is equal to C3, that is 2898 micrometer Kelvin. Okay. Now you can understand the lambda is inversely proportional to temperature. Okay. Lambda is inversely proportional to temperature. So you can see lambda is equal to 2898 by T. So he is saying that among all the radiation emitted by black body at a room temperature. So let us consider room temperature. Let us consider room temperature 27 degrees Celsius. You can consider 20 also. So this will be roughly 300 Kelvin. 300 Kelvin. So now you need to understand. So lambda is equal to 2898 by 300. So this is 300. So see, so if you calculate, just give me a second. So 2898 divided by 300. So this is 9.66 and this will be infrared. This will be infrared. And what is visible spectrum? Visible spectrum, visible range is what? 0.4-0.77 micrometer. So very important, if you want the wavelength should be 0.4 to 0.77, that is called visible range. So here it is visible light spectrum. Okay. So at the room temperature it is in infrared. At the room temperature it is in infrared. So remember one thing, if you want in the visible spectrum, the temperature should be very high. It should be in thousands. Otherwise the black body cannot radiate in a visible spectrum. Okay. So what you can see, among all radiation emitted by ideal black body at room temperature, the most intense radiation fall in the visible spectrum light. No. See, you can clearly see it is infrared. So first one is not correct. First one is not correct. This is not correct. Okay. Next. Next one. The total emissive power of an ideal black body is proportional to the square of the absolute temperature. No. So what does Stefan-Boltzmann law? Stefan-Boltzmann law. Stefan-Boltzmann law. EB, total emissive power, T raised to power 4. So not square. Not square. Okay. So total emissive power of ideal black body is proportional to square of the absolute temperature? No. It is T raised to power 4. Next one. The emissive power of an ideal black body peak at a wavelength which is inversely proportional to the absolute temperature. What is peak wavelength means? Peak wavelength means the wavelength at which the body is emitting maximum. So that is called peak wavelength. And now I already shown you that this one, this lambda is peak wavelength. Peak wavelength. This is peak wavelength and T is a temperature in Kelvin. Temperature in Kelvin. So as you can see from the wind displacement law, lambda is inversely proportional to T. Means more the temperature, the peak wavelength becomes shorter and shorter. If the body is at the very high temperature, then wavelength will start decrease. Okay, from this law. So what he said, the emissive power of an ideal black body peak at a wavelength which is inversely proportional to absolute temperature. What I want to say, this is absolutely correct. This is absolutely correct. So C is the right answer. Now go for D. the radiant energy emitted by an ideal black body, once again, the radiant energy emitted by an ideal black body is greater than the emitted by the non-black body at all temperature above 0 Kelvin. Remember one thing, the black body is a perfect absorber and perfect emitter. So any temperature above 0 Kelvin, okay, any temperature above 0 Kelvin, black body can absorb more or emit more in both the point of view. In absorption as well as emission, the black body is highest. Absorption also highest, emission also highest compared to room compared to any other body. So black body is an ideal body, a reference for the absorption as well as emission. So what is the statement D? Statement D is the radiant energy emitted by an ideal black body is greater than the emitted by non-black body at a temperature above 0. So C and D. So what I am trying to say, C and D, that is a correct answer. So C and D is a correct answer. Correct. So yes, most of the people given the right answer. Okay. So here what you need to say, C and D is the right answer. Okay. So in this case, please try to understand, this is not a single MCQ. It is not multiple choice question. It is multiple select question. It is written here, statement is R, single or plural, possible. So C and D is a right answer. Okay. Chalo. C and D will be the right answer. This is your first question, right? Now see, the beauty of MSQ is what? The beauty of MSQ is like everything they will ask in a single question. That is the beauty. And what I am trying to say, in this question, the examiner want to test your knowledge about the black body. Okay, knowledge about the black body. So if you are thoroughly in the black body, then easily you can go for answer. So C in D is your right answer. Chalo. Now move to the next one. Next question. Chalo. Everyone read the question. Everyone read the question. Now, what is the question? You can see a perfectly insulated, once again, a perfectly insulated concentric tube. Here the most important thing is counter current. Okay, so this you have to underline. Counter current means counter flow. Concentric tube counter flow heat exchanger is used to cool lubricating oil using water as a coolant. Okay, is used to cool lubricating oil using a water. Figure is given. Oil enters at outer annulus. Annulus means the gap between the two pipes. Oil enters the outer annulus at a mass flow rate 2 kg per second, with a temperature 100 degree and leaves at 40 degree. Okay. Water enters the inner tube at a mass flow rate 1 kg per second, with a temperature 20 degrees Celsius and leaves at 80 degrees Celsius. Okay. Use specific heat of oil and water 2089, 4178 in joule per kg Kelvin respectively. There is no phase change in both the streams. So both the fluids are not under phase change. Under steady state, the number of transfer unit is. What is the number of transfer unit? NTU. Now, here, first you have to separate the data. You have to separate the data. So in this case, the hot one is oil and the cold one is water. So first separate the data, right? Now, here the hotter one, this will be the 100 degrees Celsius, TH2, that will be the 40 degrees Celsius, right? And mass flow rate of the hot is 2 kg per second, and specific heat of hot CH is 2089 joule per kg Kelvin. This is the data. Now for cold one, for the cold one, what is the data? Leaves. So water enters, mass flow rate of the cold one is 1 kg per second. 1 kg per second. Temperature TC1 is 20 degrees Celsius and TC2 is 80 degrees Celsius. Okay. 80 degrees Celsius, right? And the specific heat of the oil and water, this is 4178. So this is 4178 joule per kg Kelvin or degree Celsius, doesn't matter. Now, very important thing, please listen. The most important thing is we need to check which fluid have C minimum. Always remember, any problem of the heat exchanger, first you need to be very clear ki which fluid have minimum heat capacity rate. Very important that is. So if you check here, 2089 multiplied by 2 and mass flow rate m dot c cc both are same. So in this case, it's a special problem. In this case, if you observe mass flow rate into specific heat, this product and this product both are same. You can cross check. 2089 multiplied by 2 and 1 into 4178. So in this case, this is the special thing. This is the special thing, and it is in this case, no one is C min, no one is C max. So both the values are same. That is 4178. Correct. So that will be watt by Kelvin. If you multiply this, m dot HCH or m dot CC. So this product is called heat capacity rate. Actually, the fluid which have lower heat capacity rate undergoes large temperature variation. So mass flow rate into specific heat, this product, if it is less, then that temperature will be more, change will be more. So this both are same. So in this case, there is no fluid having minimum or maximum, both are same, right? So in this case, listen, so in this case, C min and C max both are same, okay? Now, and it's a counter flow. So C min is equal to C max and counter flow. So it's a counter flow. So if it is a counter flow, then temperature profile linear. Temperature profile is linear and parallel, right? So this standard result, okay. So hope you know this, right? I am expecting that C min is equal to C max and it's a counter flow. So temperature profile is linear and parallel. Derivation, we don't have time that much to derive. This is the case. Now, so if you do that, this one, so listen. So in this case, you need to draw linear. So this is the graph, right? So this is TH1, this is TH2, this is TC1, this is TC2. So this will be 100, this will be 40, correct? And this will be 20 and that will be 80. That will be 80. So this is your delta T1, that is 20. This will be your delta T2, that will be your 20. So both are same. So if you calculate the LMTD, that is delta T1 minus delta T2 upon ln delta T1 by delta T2. So this will come 0 by 0, that is indeterminate. Okay, so that is indeterminate form. So we have to apply L'Hospital rule. L'Hospital rule, and after this mathematics, you will get LMTD is equal to delta T1 is equal to delta T2, that is nothing but 20. So this is your LMTD. Okay, this is your LMTD. Now, right? So remember, this is the very special case where examiner target on this special case, right? So what you need to do, suppose if you apply Q is equal to, you can write m dot h ch th1 minus th2 is equal to UA LMTD. You can write like this, or you can write cold fluid also, no problem. So now you tell me, let us say this I am taking C min, TH1 minus TH2 is equal to UA LMTD. Very good. Now, what is NTU? NTU is a dimensionless group which measure the size of the heat exchanger. So UA by C minimum. So you will get TH1 minus TH2 upon LMTD. Okay. So 100 minus 40 by LMTD how much? 20. So this will be 60 by 20. This will be 3. This will be 3. So here you can say NTU, that is UA by C mean, is equal to 3. This is your answer. This is your answer, right? Now see NTU. NTU is a dimensionless group of UA by C minimum. UA by C minimum, but nowhere the U value is given. Overall heat transfer coefficient not given. Area also not given. C mean also not given. So don't struggle in the question to find U and A. So if you apply the energy balance, of course, if you have doubt, ki sir, why you took only hot? If I take cold, is it okay? You take cold also because it is same. So m dot C Cc Tc2 minus Tc1. Ultimately what? The temperature drop is same. You can see here 160, 80, 20. In both the side it is 60 degree only change. Both the fluids are changing by 60. So even though if you take here Tc2 minus Tc1, still it will come 60 by 20. That is answer 3 only. So NTU is 3 in this problem. Okay. So the first of all, always remember in any heat exchanger problem, first you have to target which fluid have C minimum. That you have to cross check, and it is a case where both the fluid have equal heat capacity rate and it's a counterflow. It's a counterflow. So that's why you will get this thing. Okay. So answer is 3. Is it clear everyone? Is it clear? Respond. Is it clear? Respond. Okay. Chalo. If it is clear, please respond so that it will be easy for me that you are following. Chalo. Now, this is the question from heat exchanger, right? Now, read everyone. I request to all of you, read this question. Read this question. Okay. See, what is the question? A fluid is flowing steadily. Once again, a fluid is flowing steadily under laminar condition over a thin rectangular plate. So the key point is here, it's a laminar over a plate. So it's a external flow problem. It's not a pipe problem. Okay. At a temperature Ts as shown in the figure below. The velocity and temperature of the free stream U infinity and T infinity respectively when the fluid flow is only in the X direction. Key point. Hx is a local heat transfer coefficient. Okay, when the fluid is flowing only in X direction, then heat transfer coefficient is Hx. Similarly, when the fluid is flowing only in the Y direction, okay, is the corresponding local heat transfer coefficient. In Y direction, heat transfer coefficient is Hy. Use the relation Nu is equal to 0.332 Re raised to power 1 by 2 Pi raised to power 1 by 3 for the local convection coefficient. So for both the conditions, whether it is X direction or Y direction, for both the condition use this one. Nu, Re, Pr respectively, an appropriate Nusselt number, Reynolds number and Prandtl number. Okay. The average heat transfer coefficient are defined H bar L 1 by L 0 to L Hx dx, HW 1 by W 0 to W HY dy. Very good. If width is 1 meter, length is 4 meter, the value of ratio of HW by HL. It's a NAT question, right? Okay. So it's a NAT question. Now, what to do in this case? What to do in this case? So listen, see, this is the plate, okay? This is the plate. So now let us say the fluid is flowing in this direction, right? So somewhere you will get Hx, and this is your length. So in this case, the boundary layer grow like this. So please try to understand, this is delta. So in this case, delta is a function of x. So LC is equal to L, okay? So Reynolds number is equal to rho u infinity L by mu. So this is the Reynolds number, clear? So this will be the Reynolds number, right? Now this is the Reynolds number. So here Nusselt number is equal to H bar L by Kf, right? So if you see this number, Nu is equal to 0.332 Re raised to power 1 by 2 Pr raised to power 1 by 3, right? This is the expression. So substitute here. So please try to understand. If you write like this, Hx x by Kf 0.332 rho u infinity x by mu raised to power 1 by 2 Pr, that is mu Cp by K 1 by 3, clear? 1 by 3. Now, so you can see the relation Hx is directly proportional to x raised to power 1 by 2 by x. So Hx directly proportional to x raised to power minus 1 by 2. So this will be your relation. This will be your relation. So Hx is directly proportional to x raised to power minus 1 by 2. So if you calculate h bar, that is 1 by L, 0 to L, Hx dx. So substitute that 1 by L, 0 to L. So just wait a minute. Okay. So I can write like this, Hx is equal to some constant x raised to power minus 1 by 2. C is some constant. C is some constant. Now, so what you can write, h bar 1 by L, 0 to L, Hx dx, h bar 1 by L, 0 to L, Hx. That will be Cx raised to power minus 1 by 2 dx. So now what you can write, h bar is equal to 1 by L. So C is outside, 0 to L, x raised to power minus 1 by 2 dx, right? So this is C. So h bar is equal to C by L. This will be x raised to power minus 1 by 2 plus 1 minus 1 by 2 plus 1 limit 0 to L. So what you can write, h bar is equal to minus 1 by 2 plus 1, 1 by 2 to 2C. This will be L raised to power 1 by 2. Okay, and this divided by L, this will be minus 1. So h bar is equal to 2CL raised to power minus 1 by 2. So this is your h bar. Where? In what direction? In x direction. Suppose if everyone pay attention. So let us say if the fluid is flowing like this, width like this, if the fluid is flowing like this, right? So your LC will be W, LC will be W. So Reynolds number will be rho u infinity W by mu. Nusselt number will be H W by K. So similarly you will get, this is with respect to x, this is with respect to y, 2C W minus 1 by 2. So this I am giving you up to the, like you do this. Again you do the same thing. Wherever there is a x, wherever there is a x, instead of x substitute the width. That's it. So you got this expression. So what question he asked? HW by HL. HW by HL. So we have both the expressions. So this is nothing but your HW. 2C W raised to power minus 1 by 2. This is nothing but your L. 2C L raised to power minus 1 by 2. So your H bar W, H bar L is equal to 2C W minus 1 by 2, 2C L raised to power minus 1 by 2. So H bar W by H bar L is equal to W by L raised to power minus 1 by 2. So H bar W upon H bar L is equal to, what is width given? 1. Length given? 4. So this is 1 by 4 raised to power minus 1 by 2. Okay. So I think this will be 2. Check everyone, what's the answer? Check, this is 2. So HW, check everyone. HW by H bar L is equal to 2. Check everyone, is it correct? Everyone got at the answer 2? Respond everyone. Okay, everyone got the answer 2? Please respond. Your response will motivate me to take the new questions. Okay. So the answer is 2. And remember, many of the students are brilliant. They can directly convert here only HL by HW. So directly they will write L by W, something like that. Directly they can convert here only. Here only they will make the ratio HW by HX is equal to W by L raised to power minus 1 by 2. But I am teaching this for everyone. That's why I am taking this step. But this step is not required if you know already the result. Okay. So this is for beginners. I am saying that this is the way to derive. And finally you will get HW by HL is 2. Okay. Chalo. Now move to the next question. Next question. One side of a solid food block. One side of a solid food block of 10 centimeter thickness. Okay. So this is the 10 centimeter thickness. Sorry, this is 10 centimeter. So 0.1 meter. Is subjected to heating medium having film heat transfer coefficient. Film heat transfer coefficient means heat transfer coefficient only. So let us say this is HI, that is 70 watt per meter square degree Celsius. And other side food block is being cooled by the medium. So heat transfer coefficient HO is 100. Dear student, remember it's like a oven. It's like a oven. So whatever we will keep inside the oven heat transfer coefficient is different. Outside the oven heat transfer coefficient is different, right? So the food block is having thermal conductivity. This is food block having thermal conductivity 0.2 watt per meter degree Celsius. The contact area of the block available for, so whatever the area is there, that area is 1 meter square. The heat transfer rate in the block at steady state. So at steady state, this is Q. What is that? How much it is given? So this one is 100 joule per second, means it's 100 watt. The temperature difference between the two sides of the block in degree Celsius. So what is the temperature difference between two sides of the block? So this is the one side and this is the another side. So student may get confused, ki sir, did he ask the wall temperature of the food? No. He did not ask the wall temperature. Otherwise he will say ki the temperature difference between the two sides of the food means one surface and another surface. But what he asked, the temperature difference between two sides of the block. Okay, so right here it is one side given. So here it is one side given, right? So this side having heat transfer coefficient 70 and other side. So what he asks, the temperature difference between the two sides of the block. So overall temperature we need to find. So it's a very simple question, I know, but what I'm trying to say, every question is not difficult in the exam. So these are the very repetitive question, that's why I'm solving. So this temperature we don't know. So let us say this is T infinity I, this is T infinity O. This resistance 1 by Hi Ai, this is L by Ka, this is 1 by H naught A naught. And whether it is inner area or outer area, both are same 1 meter square. So by this way there is an entry of heat. So I can write like this, Q is equal to T infinity I minus T infinity O by 1 by Hi Ai plus L by Ka plus 1 by H naught A naught. So this T infinity I will substitute the data. So this will be 100 T infinity I minus T infinity O by 1 by, what is Hi? This side, 70 into 1 plus thickness 0.1, thermal conductivity 0.2 into 1 plus 1 by, this side is 100 into 1. So T infinity I minus T infinity O, you will get. I need this answer. Everyone, give me this answer, calculate. Everyone, calculate and give me answer. Calculate and give me answer. Calculate. Check this one, 52.4 something. Everyone please check. I will also cross check. Okay, 52.4 is correct answer. Okay, chalo. Correct. 52.4 something is the right answer. Okay, chalo. Now, this is the very simple question, but what to do? Many times is asked. Again, one more repetitive question is there, this one. I will solve fast. Now, heat gain is occurring through a composite cold storage wall. Okay, once again. Heat gain is occurring through a composite cold storage wall made of brick and polyurethane foam insulation. Okay, so let us take, so let us say there are two surfaces. So this is first one, that is brick, and this is second, that is polyurethane something. Foam insulation, thickness and thermal conductivity given below. If the exposed surface of the brick and insulation are 45 and 10, so brick exposed from this side, so this will be 45, and let us say this is T2, what is that? 10 degrees Celsius. The temperature at the interface of the brick and insulation, so this we want Ti. This is very repetitive question, but what to do? Many times it asks, so that's why you need to solve this one. So brick thickness L1 is 0.1 meter and L2 0.15 meter. This thermal conductivity K1 0.30, K2 0.05. Okay, simple, very simple funda. There are two resistances, both are conductions. So this is T1, this is T, this is T2. So this one L1 by K1 A1, L2 by K2 A2. Under steady state, everywhere the heat transfer is same. Okay. So what we can do, we can write like that, T1 minus T upon L1 by K1 A1. This is T minus T2 upon L2 by K2 A2. Area is same. T1 is 45 minus T upon L1 0.1 by K1. K1 0.30. T minus T2 10. L2 0.15 by 0.05. So give me answer T in degree Celsius. Make sure the answer should be less than 45 and greater than 10. Answer should be less than 45 and greater than 10. So give me answer of this. Everyone, please give me answer. Just you have to compare and give me answer. I am waiting for your answer. Please give me, so that I will move for the next question. What's the answer, Ray? Answer. Please find out this answer. Okay. Anyone with the answer? I am waiting for your answer. Okay. Please check answers. Is it 40? Okay. Chalo. We'll move to the next problem. Just I need to check answers. Minus 10 upon chalo. So this is 41.5. Check everyone. It is not 40. It is something 41.5. Please cross check answers. This is 41.5. Okay. Chalo. Next. These are simple questions. Now next one. Water flow tube of pipe diameter 0.02 meter. Okay, so it's a internal flow problem. So again we came to convection. Reynolds number for the flow, that is 1000. So it's a laminar flow, of course. Laminar. The pipe is heated from outside with a uniform heat flux. So that is Q. The flow and the heat transfer are steady, fully developed. The thermal conductivity of water. So K of fluid 0.66 watt per meter Kelvin. The convective heat transfer coefficient. Listen carefully. For laminar fully developed, laminar thermal fully developed for for constant heat flux boundary condition. Constant heat flux boundary condition. What is the standard result? So this is 4.36 K by D. And if it is a constant surface temperature, this value will be 3.66. But it is a constant heat flux, so it is 4.36 K by D, standard result. So here H is equal to 4.36. What is K? K is 0.66. 0.66 by diameter 0.02. So anyone give me answer first? Anyone give me answer fatafat? So what will be the answer? So if I calculate this one, this is 143.88 watt per meter square Kelvin or something. Please check. What's the answer? It should come 143.88. Is it correct, everyone? Chalo. Okay. Move to the next question. Two plane parallel surface exchange heat by thermal radiation. Okay. So let us like this. So there are two surfaces exchange thermal radiation. A radiation shield is inserted between, and it is written A. A radiation shield is placed in between. So let us say there is a shield. This is shield. Okay. All surfaces are black. So this is epsilon 1, epsilon 2 shield. All are same. All have same emissivity. Same emissivity. That is nothing but 1. All have same emissivity, that is 1. The ratio of Q heat transfer rate between surface with and without shield. So it's a standard result. When all the surfaces have same emissivity, so what you can write? Q with shield by Q without shield. Without shield. That is 1 upon n plus 1. When all the surfaces have same emissivity, so you will have 1 upon n plus 1. And he is talking about A radiation shield, that is nothing but n is equal to 1. Okay. So here you can write Q with shield by Q without shield is 1 by 2. So that is 0.5. So in this case 1 by 2, 1 by 4, 1 by 6, 1 by 8, no. So go for answer A. Go for answer A. Okay. So it's a straight away. Here the examiner want to confuse by giving all surfaces are black. So even though all surfaces are black, but when both the surfaces and the shield have the same emissivity, so you will get Q with by Q without shield is 1 by n plus 1. So that is a standard result. So that will be 1 by 2. Okay. Now read this question. This question. Two circular surfaces A and B with a value of emissivity epsilon, temperature and respective wave factor are shown in the figure. Okay, shape factor also given. Consider heat radiation only between two surfaces. So between A and 2 there is a maybe vacuum. So because of that there is only radiation. So data are given. Stephen Boltzmann constant sigma 5.67 10 raised to power minus 8. The net heat flow rate by radiation from the surface A in kilowatt. Round off to 1 decimal place. Only 1 decimal place. So always remember, so this is a plate, circular. So let us call it as this is 1 and let us call it as this is 2. So they are circular. So A1 is pi r square, pi by 4 d square or pi r square. A2 also circular, so that is pi r square. If you see the radiuses, radius is 1. So r is 1, so A1 is pi, A2 also pi. Why? Because radius is 1. Okay. And here T2 is 500 Kelvin, epsilon 2 here 0.8, here T1. I am calling as below 1 is T1. This is 800 Kelvin, epsilon 2 is 0.7, 0.7, right? And A to B shape factor given 0.17. So F12, that is 0.172, 0.172. So we need to calculate the net heat flow. Now always remember between two surfaces. So there are how many resistances? 3. 1, 2, 3. So this one 1 minus epsilon 1 by epsilon 1 A1. This will be 1 by A1 F12. And this will be 1 minus epsilon 2 by epsilon 2 A2. So if you want Q net between these two, so you should write EB1 minus EB2 by 1 minus epsilon 1 by epsilon 1 A1, first resistance, then this one 1 by A1 F12, 1 minus epsilon 2 by epsilon 2 A2. Right. So you can write like that, Q net is equal to sigma T1 raised to power 4 minus T2 raised to power 4 by 1 minus epsilon 1 by epsilon 1. So here I can write only pi. Area is pi. R square is 1 plus 1 by pi F12 plus 1 minus epsilon 2 by epsilon 2 pi. Okay. Just substitute the value. You want Q net. So this will be 5.67 10 raised to power minus 8. This will be 800 raised to power 4 minus 500 raised to power 4 pi. 1 minus 0.7 by 0.7 pi plus 1 by pi. What is shape factor? 0.172 plus 1 minus, this will be 0.8 by 0.8 into pi. So this I want in kilowatt. Anyone please give me fast? This is the answer. Anyone calculate? So 5.67 10 raised to power minus 8 in bracket 800 raised to power 4 minus 500 raised to power 4 divided by 1 minus 0.7 upon 0.7 pi plus 1 by pi into 0.172 plus 1 minus 0.8 by 0.8 into pi. So this I have to divide by 1000. So this is 1 decimal point 9.5 kilowatt. This is the answer. Let me check. What is the answer? What is the answer? Check. Is it correct or not? 9.5 kilowatt. 9.5 kilowatt. Please check everyone. This answer should be 9.5. I calculated just now. 9.5 something is coming. I may be wrong. Okay. Please check. Cross check. Please cross check. Correct. So 9.5 is the right answer. Okay. So whenever there are two surfaces are there, you just draw the resistances, you will get the answer. Okay. Right. 9.5 is correct. Very good. Now next one. Air at a 300 Kelvin. Air at a 300 Kelvin is pass at a mass flow rate 1.5 kg through a metallic tube. So it's a tube problem. Right. So the air is flowing here. So let us say Ti is 300 Kelvin. Mass flow rate inside 1.5 kg per second through a metallic tube. So this has a diameter D, how much? 0.08 meter. The inner wall temperature of the tube is maintained. So Ts is 700 Kelvin. Temperature leaving. So from here there is a TO leaving, that is 600 Kelvin. Okay. Entry is 300, exit is 600, and surface temperature 700. Occurs entirely by steady state convection. Length of the tube. Heat transfer coefficient given, that is 500 watt per meter square Kelvin. Specific heat, C, 1080 joule per kg Kelvin, and pi value is anyway 3.14 given. So remember, in this case, listen carefully. Okay, for thermal fully developed, and for constant surface temperature boundary condition. Constant surface temperature boundary condition. Right? What you can write? There is a standard derivation, TO minus TS upon Ti minus Ts e raised to power HPL by m dot C. P is perimeter. So what we can write? We can write ln TO minus Ts upon Ti minus Ts minus H. This will be pi d L m dot C. So ln, what is outlet temperature? 600. Surface temperature 700. Entry 300 minus 700 minus H. H is 500. 500 pi. Diameter 0.08. Okay. So 0.08 multiply by length upon mass flow rate 1.5. But specific heat should be in joule. So already it is given 1080. Just you have to calculate length in meter. Anyone give me? Anyone calculate this? 600 minus 700, 300 minus 700. Okay. Multiply by 1.5, 1080 divided by 500 pi 0.08. So this is your answer. How much? So this is coming to be 7.87 meter. Everyone cross check. Everyone cross check. Is it correct? Everyone give me answer. What's the answer? Or is it correct? Whatever I got the answer 17.87 correct or not? Please cross check and respond. This calculation you have to do. Is it correct, everyone? Everyone got 17.8? Respond. Calculate, everyone, and I need an answer. I need a confirmation from your side that answer is 17.8. Everyone, I need answer from you. Okay. Okay. So answer is 17.87. Answer is 17.87. Okay. So now these are some questions we solved in a last 1 hour. Okay. Now this is the problem for your practice. So take this problem as a practice and try to solve. This is from unsteady state. This is from unsteady state. So you can take the screenshot or you can stop the video and you can solve this problem. So this is from unsteady state. Already the Biot number less than 0.1. So it is a lump heat capacity method. There are both the bodies and necessary information is given. You need to find d1 by d2 ratio. Okay. So this one question I leave for you so that you can practice. So this is the session. In the last 1 hour we solved some couple of questions. That's to overview what is heat transfer. Hope this session help you a lot, and like this many sessions are upcoming, so don't worry at all. Whenever you are in trouble, feel free to reach to us. Okay, so I am the employee of ESE Engineering Academy. We will provide the live lectures, recorded lectures, offline classes and many more. For the further explanation you can go to the website and you can cross check. Okay, so that's it from my side. Thank you very much for listening me quietly from the last 1 hour. Okay, so thank you everyone. Have a good day.